Now, dear student, thermal properties of the matter and the thermal. Today we have the topic for the discussion, that is thermal expansion and the types of the expansion along with their types of the coefficient. Okay. Now, what do you mean by the thermal expansion? So I have mentioned the some words regarding to the thermal expansion. So we have the basic information that all that matter exists in the solid, liquid and gas. As we are just giving the heat to them, that mean they are associated with the concern of the heat, is that so they have the tendency to expansion. That mean there is a increase, probable increase in their size is there. Okay, so this tendency of the increase in the size on heating them is called the thermal expansion is there. And basically we have the three types of the basic expansions can be there. First is the linear expansion, and how can we discuss it? Now we have the first expansion, that is called the linear expansion. So simply we can add the word here: increase in the length of metal rod or the wire on heating is called the linear expansion. So here we have on the given temperature, the length of the rod is the L is there, as we are just giving the heat to this rod is there. So definite there is a expansion of the rod in the either side. Okay, so the new length of the rod is the L dash is there. So as we want to make the find the change in the length, so L dash minus L will makes the change in the length, that is this is the kind of the length change. Okay, so this is the simply the linear expansion we have. Now the next we have the area expansion. So what we can do for its explanation? Simply it's an increase in the area of the metal sheet on the heating. So this is the sheet which having the initial area, that is called the A is there, and on the heating there is an expansion in the sides of a that square sheet is there. So the new area, that is called the A dash is there, and definitely there is a increase in the area, that is called the delta A. So we can say that delta A can be stated as a final area minus of initial area. So this is the simply the meaning of the area expansion we have. Now the third type of the expansion we have the volume expansion, and definitely increase in the volume of a metallic block or the cubical block on the heating is there. So here I have made the simplest explanation of that part. So initially the cubical block having the volume, that is called the V, and on the heating there is a new volume is there, that is called the V dash, and definite this is the change in volume, that is called the delta V, that is the expansion in the volume we have. And anyone is saying that what is the possible change in the volume we have, so you can write easily that V dash minus V makes the change that is in the volume, that is called the delta V is there. And as per the types of the expansions, we have the types of the coefficients are there. As we are just talking the linear expansion, so the linear expansion coefficient is there. So generally the linear expansion coefficient can be regarded as alpha L we have, as the the element having the area expansion is there. So we have the type of the coefficient, that is called the alpha A, that is called the area expansion coefficient, as there is a volume expansion is there. Okay, so definitely there is a another coefficient, that is called the volume expansion coefficient. So how can we discuss the formula of the concern coefficients? So we are starting this one. So here I have made the topic, that is linear expansion coefficient, and I am just representing it by the alpha. In the subscript we have the L is there. So here we are just imagining a rod of the length L is there. Rod of length L at room temperature. Okay, so we are just giving the heat to it. Okay, so probably there is a increase in the length of the rod we have. Okay, so this is the new length of the rod, that is called the L dash we have. Okay, so what is the possible that mean increase in the length we have? Okay, so here we can say that L dash minus L makes the concern of the increase in length we have. Okay, now increase in length, that is called the delta L, that is called the L dash minus L, depends upon following factors. So what are they? That is called the delta L, that is increase in the length, that is called the delta L, is directly proportional to the temperature, as whatever the amount of the heat we are giving to it, so its a temperature rises up is there. Okay, now delta L is directly proportional to the initial length of the rod is there. Okay, so whenever we are just mixing or combining these two terms, this is the equation number 1 and this is the equation number 2, that is called the delta L is equal directly proportional to the L delta T. So here we are just using the coefficient and removing the proportional sign. So I am just writing it, that is coefficient, that is called the linear expansion coefficient, that is called the alpha L and L delta T. So as we are just making the consideration of the alpha L is there, we are just separating it. Alpha L is equal to, that is called the delta L upon L delta T. So here we have alpha L is the linear expansion coefficient. Okay, that is equal to increase in length is to be divided by original length into rise in temperature, as we can write here, that is the rise in temperature we have. Okay, now the another one segment, that is a unit concept. Units of alpha L we have, and these are in the SI system and the CJ system. Okay, so Kelvin inverse in the part of the SI system we have. Okay, this one is the available in the SI system, and as we are just using the degree Celsius minus 1 in the CJ system. Okay, so this is the possible representations of that part we have. Now we have the area expansion coefficient, and we are just using it in the part of a symbol, that is called the alpha A is there. So we have initial area of sheet, that is A is there, final area of sheet after heating, so rise in temperature delta T, that is called the A dash we have. So generally we are just using the simplest segment, that is called A dash minus A, that is called the delta A, that is increase area we have. So we can say the increase in area, that increase in area we have, that is called the delta A is directly proportional to that is delta T we have. That's the one of the basic equation we have, and most probable we will use the same pattern as we can understood in the easier manner, and the delta T and the initial area whatever the we have given, so it also depend upon the on that part, and we are just combining the 1 and 2, so delta A is directly proportional to the A delta T is there. Okay, as we are just removing the proportional sign, so we have that is called the delta A is equal to A delta T. Here I am just representing the coefficient of the area expansion coefficient, that is called the alpha A is there. So the alpha A can be stated in the part of that delta A upon A delta T, that is called the increase area, increase in area is to be divided by original area into a rise in temperature. So this is the simplest that mean representation we are using here. So probably we have the units. So two types of the units we have, that is called the Kelvin inverse and the degree Celsius inverse we have. These are the units we have. Okay. Now we have the third coefficient, that is called the volume expansion coefficient. Volume expansion coefficient, so we are using the alpha v is there. So definite we are just assuming a rectangular cubical block we have. So probably there is a increase in the volume on the heating we have. This is the cubical box section we have, and we are just giving the delta q amount of the heat to it. So what will happen, probably there is a increase in the volume we have. Okay, increase in the volume we have, that is called the delta v we have. This is the initial volume and this is the final volume we have, that is called the v dash. And probably how we are just making the assumption of this coefficient, so we are using the same pattern thing we have, that is called the v dash minus v. It makes the concern of the delta we have, that is called the increase in the volume, and the delta v is directly proportional to the delta t is the delta v is directly proportional to the original volume is there. So delta v is directly proportional to the v delta t we have. Okay, so this is the simplest portion we have, and I am just removing the volume coefficient of proportionality. So I am just writing the v delta t, and I am just writing it in a separate manner so you can easily understand it. So alpha v we can write here, that is called the delta v upon v delta t. So possible units we have, that is called the degree Kelvin, Kelvin inverse is there. Okay, and same how we are just using the degree Celsius inverse we have. Okay, so we have here, I am just removing the degree sign is there. Okay, Kelvin inverse and the degree Celsius inverse is the possible unit. So same how one of the thing, one thing is the common in the all type of the coefficients, that is unit is the same we have, and the same pattern formula we are just getting in the part of the ratio of the length, area, and the volume, and the concern of the temperature we have. So this is all about the that mean volume expansion all the coefficients we have. Now here we have one of the graph which is given in the NCERT book, that variation of the volume expansion coefficient with the temperature. So we are just taking the standard graph of the volume expansion coefficient. So for a given substance, the that alpha v varies with the temperature, ensuring the coefficient of the cubical expansion all the or the volume expansion coefficient. So the value of the cubical expansion or the volume expansion coefficient first increase with the increase in the temperature, but near about the 500 degree Kelvin temperature, it almost the having the constant value. Okay, or the as we are just further making the increase in that part, so it becomes a very constant value. It has a very constant value for the with the rise in the temperature, because we can see that the 250 to 500 degree Kelvin, 500 Kelvin, there is a no concern of the that mean too much change in the value of the volume expansion coefficient. And even you can go with the table which is given inside the NCERT book, where you can make the that mean knowledge of the volume expansion coefficient. And I can show you the volume expansion coefficient in the NCERT book. We have this is the page number 278 we have. Okay, so the so many values of the different metals is given, and they are just getting the expansion on the heating we have. Okay, as I am just reading that aluminum having the 7 into 10 to power minus 5 is there, brass having 6 into 10 to power minus 5 is there. Okay, as we have the iron is there, so 3.55 into 10 to power minus 5, 10 to power minus 5 power is there. Okay, so these are the, that mean coefficient, and including the invar, mercury, water, alcohol, and all the things we have given here. Okay, so basically we are just using these kind of the coefficients to make the some commercial applications, so we will discuss it here. Now here we want to make the another that mean volume expansion coefficient of an ideal gas. So we know the ideal gas equation, and already you are just reading, doing the study of the, that mean ideal gas in the chemistry. So ideal gas equation we have, that is called the PV is equal to nRT. That's the one of the, that mean basic equation we have given. Now differentiate equation 1 at constant pressure with respect to temperature. So what kind of the possible result we are just getting here, so we will discuss here, that is called the that is P, and one of the portion with the pressure we have the 0, that is called here the n and the r, these are the constant, and with respect to temperature we have the variation, that is nr, and the delta t with respect to delta t is there. So we are just making the cancellation of this part, so we are just getting p delta v, that is equal to nr of delta t is there. So this is the equation number 2 we have. Now we are just dividing the equation number 2 by the equation number 1. So what we are just getting, P delta V is equal to nR of delta T, okay, is to be divided by PV upon nR, and the T is there. So n to n cancel, r to r cancel, and we are just making the separation, and following P to P is also cancel. So we are just getting and making the simplification of the formula delta V upon V, and keeping the 1 upon delta T is here, and that is equal to the 1 upon T, and this whole fraction is work like an volume expansion coefficient. So I am just making the replacement of that part, and I am just writing that the alpha V is there is 1 upon T. So simply, as we are just increasing the temperature, so volume expansion coefficient of the ideal gas, or the alpha V decreases as we are just increasing the meaning of the T is there. Okay, and same concern which is which we have already developed in the parts of the that mean solids we have. Okay, so this is the all about the different types of the thermal expansions, linear, area, volume, and their concern coefficient of expansions.